So in the last video, I left off where we had designed this 2 to 4-bit decoder. And then I asked the question, well, how can we use this decoder to make a 3 to 8-bit decoder? Could I then use this decoder to make a 4 to 16-bit decoder? Well, what about the enables? How are the enables going to play into this? Well, in this video, I'm going to answer all of those questions. So the way we begin this process is we need to first think about the truth table here. So if we look here, we have this truth table and we see that in the output we have 0 to 3 bits. So that's a total of 4 bits, but we want to double it when we make our 3 to 8-bit decoder. So, and then you'll also notice that we only have, if we count these two, these are the only inputs that directly correlate to the output. So we would have to add an additional bit for the purposes of generating an output with 8 bits. So I have created this sort of dynamic truth table that shows how to expand the decoder. So for now, let's just ignore the green parts, the green number, because that's a second expansion. We want to look at the first expansion only. So for the first expansion, I can declare decoder number 1's output to be bit 0 to 3, right? So that's going to come here, bit 0 to 3. And then for decoder number 2 here, I want to declare that to be the output of decoder number 2, that is. I want that to correspond to bit 4 to 7. So then in the output, you can sort of consider it like decoder 1's output is appended to decoder 2's output, or vice versa. So since they're appended, now we have a total of 8 bits, which is this one here, right? So now the question is, well, if we are in this region, how does decoder 2 know it? Well, decoder 2 will be looking at this set of numbers here, and then it's going to see that it's zeros. So then it knows not to display anything there in the output, right? Likewise, if we are in this region here, decoder number 1 and monitor this set of numbers here, and then it'll determine if it shouldn't display a number. So in this case, if it's monitoring this and it says that it's a 1, oh well, that 1 is dedicated for decoder number 2 and it is enabling decoder number 2. Therefore, I cannot display anything at this point here, in this area here. So in addition to the enables, one thing that we know for sure is that right here, if I circle this set of inputs is directly related to this set of outputs. Likewise, this set of inputs is directly related to this set of outputs, except it's on decoder number 2. And actually, you can keep going down this table and you'll see that this is the case for all of these expansions. So really, it's just a matter of where we place the outputs of our decoder. And then we need to worry about how to incorporate the enable button or the enable pin into this system. So I'm going to go ahead and draw a schematic, and then I'm going to show you what it looks like when we combine 2 decoders into a single module. So this is actually what the wiring now looks like. So you'll notice that on the left here we have our inputs. So this time we have B, and it's going to be 4 to 0. So another thing, we see that these two decoders rely on these 2 bits here, B0 and B1, right? Basically, I guess these are kind of labeled not perfectly. Let me fix that. So it's like sort of like that, right? And it's going, B0 is going to A0 and B1 going to A1, as well as B0 goes to, if I follow here, goes to A0 of the second one, likewise with B1. Okay, so for the purposes of understanding what's going on here, let's make pretend that these AND gates don't exist. So let's make pretend we have a wire straight through here, and then a wire straight through here. So if you remember, B2, this bit here, is the bit that determines whether or not each decoder is on or off. So let's look at the case when B2 is 1. So if B2 is 1, if we follow here, this line, we see that it goes directly into the decoder number 2, and it's going to enable it. At the same time, it's going to go through this inverter. It's going to turn it into a 0, and then it's going to disable decoder number 1. So this takes care of, making sure that I don't display both of them at the same time, or I don't activate or enable both decoders at the same time. Likewise, if I have a 0 coming in here, right here, it's going to disable decoder number 2, but then it's going to enable decoder number 1. So I want to create additional functionality in this entire module, however. So so now these AND gates come into play. So what you'll see here is that I have an AND gate that goes into the decoder number 2, as well as the AND gate that goes into the decoder number 1. And the way this works is that, so then I can say that, okay, B3 is going to be my enable pin for the entire module. So then the way that works is that, let's suppose we have a 0 coming into the enable. So that means that this logic gate is no longer going to have an input, a logic high as an output. Likewise, this logic gate is also going to have a 0 as an output. So it's going to, in fact, disable both decoders. Well, I wouldn't say disable, but, well, I guess, yeah, disable works. So on the other hand, if we have a logic high in the enable pin, what that means is it's simply going to pass along whatever value is located on this pin. Whatever value is located on this pin, it's going to pass it along. So let's say this pin is 1, we're going to get, so let's say we have a 1 here, and then we're going to get a 1 here, right? 1 like that. But if it's a 0 here, it's going to be a 0 here. So it's simply passing it along whenever the B3 pin is enabled. And that's how the enable of the entire module works. So now we can write some expressions, actually. So then I can say the following. So let's say if I point to this pin here, I can say, all right, I'm going to call that W of W2, right? And then I'm just going to say that is equal, and then obviously W is simply an internal variable. And then that is equal to inverted V2 multiplied by V3. And then this one, I'm going to call it X. It's just another internal variable. So X of 2 is now going to be equal to B of 2 and then B of 3. Just like that. Okay, so now let's go to the ModelSim software. And now what we want to do is we want to create some new modules. So I'm going to say add to project, new file. I want to place it in the source. And I'm going to call it DC 3x8. And then language is going to be Verilog. And then additionally, I want to make test bench for this 3x8. So I'm going to put it in the TB folder, SystemVerilog. And then I need to give it a name. Let's call it DC 3x8 underscore TB. Okay. Okay, so now I'm going to go to edit the 3x8. And we have an empty document here. So now we can begin our module. So I'm going to say Then I'm going to call it DC 3x8 after the file name, of course, in the module. So I want to now declare some variables. You know how this goes. So then I say input logic create a 0 for B, comma, and output is going to be, I can say output logic, and that's going to be 7 to 0 because we have 8 bits now. So then we end that and then we put a semicolon right there. So the next step is just very straightforward. So let's remember that I want to declare some internal variables, right? And then I'm going to call them W. And I can do this in the same line, but this is just to reiterate. Each of these is 3-bit inputs. So these are my internal variables now. Now what I need to do is I need to assign something to them. So let's start assigning W0. So W0, if we look at our schematic here, we want to simply pass along the value of B to the first decoder, as well as the value of B1 to A of 1. So I want to like pass that value straight forward, and then when I get to the second decoder, I want to just pass that value straight as well. So I have assigned each of these values to the value they correspond. So W0 corresponds to B0, W1 corresponds to B1, and then W2 actually corresponds to inverted B2 and B3. And then for X, you know, I pass along the same values again. X of 0 equal to B of 0, X of 1, B of 1, X of 2 is, and then X of 2 is B2 and B3. So now I have to, this is where I now instantiate the previous module that I made. Okay, so now I want to instantiate the previous module, so then I say DC 2x4, I'm going to call it DC1, and then I'm going to say W2 to 0, so that's 3 bits, square bracket, and then I want to declare the output of this instantiation, so that's going to be 3 to 0, and we close that. Let's see, did I do that right? Yeah. And then I want to instantiate the module once again for the second decoder, and then I'm going to call it decoder number 2. And then it's going to be, this one is going to be with X now, so that's going to be X 2 to 0. And then the output bits is actually going to be from 7 to 4. So this is what I was talking about, how we arrange the output of our previous decoder and such that we get a total of 8 bits. So if you notice that I declared out to be 8 bits, so then now this output, the first 4 bits correspond to decoder number 1, this object here, and then the last 4 bits simply correspond to decoder number 2. That the output, of course. So that's how that works. And then we're basically done with the module. It's as simple as that. Okay, so now we want to create the test bench for this 3 to 8 bit decoder. So then let's go to the test bench file here. Let's see, so then now I want to declare the timescale. So timescale is going to be units of nanoseconds, of course. And then the step is going to be in 10 picoseconds. Okay, so then the module, I'm going to call it DC 38 underscore TB. Close that. And then we just assign some input output test variables here. 0 This is going to be test underscore in, that. And then the output, as you know, is going to be 8 bits. So that's 7 to 0. Test underscore out. And then we need to instantiate the 3 by 8 or 3 to 8 bit decoder. So then we just do that here. PC 3 by 8. Oh, and then I'm missing the unit under test. So then we know that the output of this module is B, or the input is B. So then we say dot B test underscore in. And then we know that the output is called out too. We say test underscore out. Close that. Now we just double check that we have the values correct. So we have B related to test in, and then out 2 related to test out. So we see here we have B, and then we have out 2. So that's good. So let's keep going here. Initial begin, going to be our initial values. Test, I want my test in to be equal to 0. So let's make that 0. And then I'm going to end it here. And then since we have 7 or 8 bits in the output, or rather 4 bits in the input, we want to be able to cycle through all the possible combinations, and I don't want to write each one. So then I'm going to use a little if statement here. So I'm going to say always begin, and then I'm going to add a delay here. Put that, and then I'm going to say test in less than equal to test in plus 1. So then it'll loop through, and it'll add 1 to the test in. However, I do want it to stop when test underscore in is equal to 4 bits, right? 1 1 1 1. So when the test in reaches this value, I want it to stop. So then I'm just going to say begin here, and then I'm going to say stop. I'm going to close that. Then I'm going to say end. And then I'm going to say end for the always begin, and then I'm going to say end the module. Okay, so then I verify that everything looks good. Let's go back here. Oh, looks like I'm missing an M here. Okay, but I believe this should be good. So now I'm gonna press Control Save here, and then Control S as well, and then I'm gonna compile all here. So we have some errors here. Let's see why. Okay, so I was able to compile all of my files. You know, I had an underscore here that I didn't even see for a while, and it was causing some errors. And I took it out, and then everything compiles nicely. So what I'm gonna do now is I'm gonna run this code. I'm gonna go to simulate, and then I want to select the 3 to 8 test bench here. So I'll press OK. So it loads everything up. Now we have this. I want to add this to the waves, and then I want to dedicate more space to the waves. And then I'm going to run this here. Let's take a look at what this looks like. And then I want to look at it this way. So as you can see now, when A3 is now considered the enable, so it is 0 here, so we have all zeros in the output, you know, 0 to 7, so that's 8 bits. And as we move along here, you see that it's still 0 up until the point where A3 is 1, so that's enable is 1. And then we see here there's like a little, it's like a sort of like a staircase here, and it's going up here. So And we can also look at this number change while we move to the left and to the right. So we see that 1 is sort of like shifting left and right. So this works nicely. So we finished the 3 to 8 bit decoder, but now what if I want to take this even further? Let's say I want to make a 4 to 16 bit decoder here. And so actually this is very easy to implement. We already have the 3 to 8 bit decoder, so now I just have to implement the 4 to 16, and I'm following the same principles as I did previously. So, and I already wrote out the expressions for the internal variables here. So we see G3 is equal to inverted C3 times C4, so that you can do that with an AND gate. And then likewise, we have P3 here in the bottom, the internal variable, that's C3 times C4. That's with an AND gate. And then, we see that C0 connects directly to B0 and directly to B0 of the second decoder. Likewise with C1 here, connects directly to B1 and then directly to the B1 of the second decoder. So actually this is pretty straightforward to implement. So let's go ahead and do that right now. Well, I've created the new modules here already. And actually the way we make the new module, we want to instantiate this 3 to 8 bit decoder, and we want to instantiate it twice in the 4 to 16 bit decoder. So what we can do is we basically can copy over and change some parameters. So in fact, I already did it here. You can see that it looks pretty much identical to the 3 to 8 bit decoder. So here it is. So let's go over it quickly here. So obviously we instantiate, or we begin with module DC 4 to 16, decoder 4 to 16. We have an input logic of 5 bits here. I'm calling it C. And then my output is 15 to 0, so that's 16-bit output. Call it out 3. And then my internal variables are G and P, and they're both 4-bit variables. So then I'm assigning, obviously, G of 0 to C of 0, G1, C1, G2, C2, G3, and then we reach this G3 here, right? Let's look at what we have here. So I said that G3 is equal to inverted C3 times C4. So that's exactly what I set G3 equal to here. So the difference is that we are passing one additional variable, and then the third one here is a little bit, it's almost the same, except I'm working with the last 2 bits of the input. And then I instantiate the 3 to 8 bit decoder here. I instantiate it, and I call it DC3, and I call it DC4. So now we see that this object requires 4 bits in the input and then 16 bits in the output. So what I'm doing here, I mean, this whole module requires 16 bits in the output, but this individual requires 8 bits. So when they are combined, they actually add up to 16 bits here. So this is how it works. And then similarly with the test bench, I've already written it out. I have an input 5 bits here, and then the output of 16 bits here. So let's see, that makes sense to what we have here. We have 8 and 8, so that's 16 bits. And then we are, performing the unit under test. We relate C to the test input, we relate out3 to the test. This is pretty much the same thing. And then we are, we set test input to 0. And so here we have this condition. If test in reaches this binary number, then we're going to stop. So let's go ahead and compile all of this. We have a successful compilation. Actually, I need to save it first, right? And then we can compile. Okay, so that compiles nicely. So now what I'm going to do is I'm going to go to simulate, start simulation. I'm going to go to work. I'm going to go to 4 to 16-bit decoder. I'm going to select that. And then it does the magic. So then I select these two arrays, add them to the wave, and then you can see that these are bigger than before. So let's go ahead and run this thing. Let's go back here, and then I want to view the whole waveform. So there it is. So now this confirms that our code is working correctly. We see this is basically this is 5 bits for the input. This top section here is the input, and it's going through all of the possible combinations, and then it's until the last bit, obviously, where the enable is placed in logical high, and then at that point we have what we expect to see, this nice staircase shape. So that works nicely. So, you know, we can take this further and we can even make the 5 to 32-bit decoder. So let's go ahead and do that quickly. Okay, so this is what that 5 to 32-bit decoder looks like here. Here we have a sort of simplified version of the usual way I write things. So we have these single lines, but they represent multiple bits. So this is just the easier way of representing it. And each of these boxes is now a 4 to 16-bit decoder. And then in the output, we see that there are two 16-bit lines, and it comes to a total of obviously 32 bits. So I'm going to spare you the details here, and I'll just give you the code. So this is what the code looks like here. And this is what the test bench looks like. So one thing I would like to point out, though, is that we are instantiating DC 5 to 32, and DC 5 to 32 instantiates from DC 4 to 16. DC 4 to 16 instantiates from DC 3 to 8. And DC 3 to 8 instantiates from DC 2 to 4. So it's sort of like an instantiation inception sort of thing going on. Okay, so enough talking about it. Let's run this damn thing. So I saved all of it. Let's compile all of it. So it has been all compiled successfully. So let's go ahead and simulate our work here. And we want to select the 5 to 32-bit test bench here. So let's run that. We got a couple warnings, but not to worry. And then we select our input and output. We add that to the wave. And then we run this. Okay, so now we go back here. And then since we want to be able to see this nicely, I want to look at all of my glorious 32 bits here. And then I'm going to go to View, Zoom Full. And then I want to open these drop downs. And then there it is. So this is basically the 5 to 32-bit decoder. And then, you know, once again, A5 is the enable button now. So as we move along here, we see that the output is all zeros up until the enable reaches 1 here. And then we have that beautiful sort of staircase shape. So this tells us that, you know, the code is working nicely. And obviously this top section here goes through all the possible combinations. So it works nicely.